Good afternoon, everyone. My name is Neha, and I'm part of the MEA department working under Professor Kleisel's lab, and I'm also one of the recipients of the Greer Summer Scholarship Program. For this summer, I've been working on a completely different project than I was the past year, and that was comparing grid forming inverter techniques with the UCC microgrid. So, a little bit about myself. I'm an incoming fourth year. I'm majoring in mechanical engineering with a specialization in renewable energy and environmental flows and a minor in design. My PI is Professor Jan Kleisel, and my gear mentor is Gin Chia. And the lab that I've been working with is the DER Connect Lab at the Center for Energy Research. So, firstly, we need to understand the problem. What is a grid forming inverter, and why is this relevant? Renewable energy comes in various forms. However, it does have its disadvantages. One of this being the lack of rotational inertia. This rotational inertia is the measure of an object's resistance to changes in its rotational motion, and this determines how quickly the power grid, which is supplied by renewable energy, can respond to any fluctuations within the grid. However, due to the lack of rotational inertia, they're not as quick to respond to any fluctuations, which results in issues like blackouts. And with this difficulty in managing these fluctuations, limited control and flexibility, it becomes really difficult to implement these into our modern grid requirements. So, why do we need grid forming inverters? Unlike a traditional generator, which uses the existing voltage and frequency of the grid to regulate, a grid forming inverter, however, it can maintain and establish its own frequency and voltage, which makes it ideal in scenarios where you want to implement a high amount of renewable energy sources. So, for instance, in the present, we have much more reliance on non renewable energy sources, and this results in a greater amount of generators. And with the lack of capacity to maintain renewable energy sources, we have fewer inverters. And this results in a unidirectional power grid system, which means only producers contribute to the grid. But in the future, with more developments into grid forming inverters, we can have a bigger dependency on renewable energy sources. And this decreases our reliance on non renewable energy sources, decreases the amount of generators, as you can see, and results in a bidirectional power grid system where both the producers and the consumers contribute to the grid equally. So the goal of my research the past summer has been to create and simulate grid forming inverters using two different control techniques. This is Droop and virtual synchronous generators. So a little bit about these two control methods. So Droop control is much more simple. It works for both a traditional generator and a um, reforming inverter, and here it controls the power output of either your inverter or your generator by adjusting their output based on any changes in your grid frequency or voltage. So it's much more easier to implement, but it isn't as precise because if there's any change in your damping constant, this can create much more larger deviations in your frequency. Whereas for a virtual synchronous generator, it's a bit more advanced. It has better technologies designed to simulate the behavior of your traditional synchronous generator and achieve this by creating a virtual inertia and frequency regulation. So in terms of our methodology, we've been working with the UCSD microgrid. So a little bit of context, this was modeled by our postdoc, Kohei, and it consists of 48 buses. So buses are the squares on this diagram, and it basically signifies the conductors or connection points within your nodes. It can have loads as well. And then we have three group-based grid-forming inverters, along with solar generation at 7 locations denoted by the black boxes. And the entire demand of this power grid system is 46.61 megawatts. And this is all connected back to your main power grid of San Diego, denoted by this black star, representing the SDG and E grid. And then we used a real-time digital simulator, which essentially we have a software called RSCAD where we model the UCSD microgrid and our different control techniques. And then we compile and run this and send this information to our RTDS, which gives us real-time information about any frequency regulations, the voltage, the reactive, active power, and you can adjust the set points and run various scenarios. This is the RSCAD software that I was talking about previously. So this is a section of our UCSD microgrid. It's branch 3, as you can see. And within this green box, which denotes a grid forming inverter, we have a Droop-based control system. So in terms of our results, this was our previous control that we had implemented for grid forming inverters in the UCSD microgrid. So this is a Droop control, much more simpler. It has a virtual synchronous loop. It has a reactive and active power loop. But the past summer, we've been able to develop a VSG control loop. So this consists of a power synchronization loop and a reactive power control loop, which takes care of your active and reactive power set points. And the results were favorable. So the nominal frequency of a power grid for a stable power grid is 60 hertz, and the red lines, they denote the frequency sent by the bus that connects to our main power grid, the SDG and E grid. So there's a lot of fluctuations, as you can see, but by implementing a VSG control, we can see that the other buses which connect to our specific VSG generators, the amplitude is significantly small at 60, which shows that there isn't much deviation and there is a stable frequency regulation. In terms of future directions, we want to use an existing paper to replicate the different types of disturbances. So we were looking at different scenarios. So the first one would be islanded mode versus connected. So islanded mode means we disconnect our UCSD microgrid from the main SDG and E grid and compare when it's connected and run the same type of disturbance and see their performance when we have a VSG control loop. The second is testing out different types of disturbances. For this, we'll be adjusting the inertia constant, the rotational inertia constant I was mentioning before. And then lastly, we want to check the number of generators and the location of these generators when we implement a VSG control loop and see its performance and response to any disturbances. So my research experience so far, I've learned a lot. As a mechanical engineering major, I really don't have a background in power systems, so this was really great. It was a big learning curve. And I also got to try out new technologies like RTDS and RSCAD, which is very niche and only specific to our lab. Um, I also learned how to approach literature review because our postdoc would make us go through like 10 papers a week. And that was really beneficial because it helped me better understand what kind of power grids I had to model, the advantages, disadvantages, and made it more easy to familiarize with RTDS and RSCAD. I also got the chance to collaborate with other undergraduate students and worked on different projects besides this, such as Raspberry Pi configuration and helping set up their node room in their new lab. And lastly, I really want to thank our sponsor, General Atomics, for giving me this opportunity to do my research the past summer. It's given me a chance on how undergraduate research works, as well as a glimpse into the academia lifestyle, because my future goal is to go to master's programs, and I will be applying this fall. So it gave me a glimpse onto what a master's thesis versus a PhD program would be, since I got the opportunity to talk to a lot of the grad students and postdoc students in my lab. And I'm also able to continue my research for next year through this entire program. And then lastly, I would also want to thank the following people: the DER Connect Lab, my postdoc Kohei, my gear mentor Keaton, Professor Kleisel, as well as my fellow undergraduate research interns that have supported me this past summer. Again, our summer scholarship sponsor, General Atomics, our gear program coordinator, Sarah, and then my friends and family.